Thank you. As the chair said, my name is Paul Sukpe from Imperial College. And this will be the overview of my presentation. So the context is for BS 799, which is one of the guidance for metallic structures assessment, which is mainly engineering critical assessment. So in engineering critical assessment, the main parameters, fracture parameters are the critical values of the stress intensity factor, the J integral or the crack tip opening displacement, which are used for engineering critical assessment. And normally, 3 tests are conducted. You take the lowest or the average value for your input values. But because of variability in fracture toughness, we tend to conduct multiple tests just to get a correct value or representative value, characteristic value of the fracture toughness that we can use for our assessment, for conservative assessments. But we are moving towards more modern structures, especially in the nuclear industry. And so this conservative assessment may not be appropriate. And so we're looking at the minimum of 3 equivalent, how it started. And, this was done 40 years ago. And so, like I said, there's more modernization, more sophisticated approaches have emerged. You can now use finite element analysis as well for engineering critical assessment. So it's just an overview of trying to review this method that was developed some years ago to see how we can improve engineering critical assessment. And so the basis for minimum of 3 equivalent, we are aware that, this is not well documented. It's just through experience people do. So for example, in Sharpie testing, you normally test 3 specimens. Either you take the average or the lowest. So fracture toughness, this will differ depending on the method you use. So if you use a single specimen method, you will test a number of specimens, and then you generate your resistance curve. For that, if you use the multiple specimen, the minimum will be 6 specimens to test. And then you can also generate your resistance curve in which you can derive your critical value of fracture toughness. An overview of how this methodology of minimum of 3 equivalent came into the current standard BS 7910. So this started in the 1980s by Mote, where he used crack opening displacement design curves alongside wide plate testing. So this was large testing of wide plate testing, where he incorporated safety factors into the procedure. And this was then drafted into the first published document, which was the PD 6493 in 1980. So this design curve, that time, fracture toughness, fracture mechanics was not very popular. So people were still learning on how to test materials, and also, some of the materials, especially ferritic steels, were still new in the industry. So Jottler and Garwood then continued on this using the method of design curves to try to use a probabilistic analysis to see the same level of confidence by testing 3 specimens. So improving upon moving from wide plate tests, which was complex to test, more expensive. And so they were now testing SEMB tests, which were simpler but thicker specimens. So in this case, what we should note is that constraint was not taken into account in those days. And so the second draft of this public document was drafted after Garwood and Jottler's work. And then Garwood then move on to use statistics again to imply that if we test the minimum of 3 and the same level of safety is achieved or is adequate, then we can then imply that testing more specimens or having larger data sets drive the level of the same level of safety. And so this approach was then used to draft the first BS 7910 document, which is the guidance for metallic structures. And there have been several revisions over the years to the current one, which is the 2019 edition. And so this, I've just taken it from Gao's paper. So where first we moved from a minimum of 3, which was Kamal's work. And now we use the idea of the same level of safety, irrespective of the number of tests. But the caution here is that the macrostructure or the notch failure should test the same macrostructure, which is sometimes difficult to achieve. So people tend to discard fracture specimens that do not qualify or that do not meet that requirement. And so the idea of just looking at this and revising this again, especially for high integrity components, is why we are doing this work. And so in BS 7910, it's also confusing because they are giving us 2 confidence levels. So here the confidence level is just the median fracture toughness value that was used in the past, which is the 50th percentile, which is based on this probability equation where the number of specimens here is n. And for this, it works for 3 specimens. So the minimum of 3 again, before the word equivalent came inside to give more confusion. So it also advises to use the 20th percentile where you get 50% confidence in your ECA. And what we should also note is that the scatter in the data, there's variability in fracture toughness, so the scatter should be within 70 to 140% of the average toughness. And so in BS 7910, there's a table in this format. So 3 to 5 specimen, you take the lowest value, 6 to 10, second lowest, and up to 15 specimen, you take the third lowest. But it also advises for cleavage for ferretic steels to use statistical approaches such as the log normal approach for your analysis. And so we've just done similar thing as BS 79 advises, but here we use the 5th percentile with 75% confidence, which with experience and research, it's been advised that is one of the good ones for high integrity components. So this is one of the historical data, which was also done in premise for the BS 7910, which came from the PD 6493. And so you can see this is a thick specimen. Like I said earlier, constraint is not considered here. So thickness effect, crack depth effect is not considered. So this was done for over, I think 12 laboratories in 10 European countries. So this was a large program that was tested to determine the fracture toughness in the data to brittle transition. So we're just taking one of those data sets, which is the 145 data set. And out of that, the rule for the minimum of 3 equivalent is also that the material should test the same macrostructure. It should fail by cleavage. And if by data, a small data failure. So first, the data set we look at is out of this 145, 105 of them failed completely by cleavage or brittle failure. So we plotted that on our log normal distribution, and we can see there's a good fit. And with the minimum of 3 equivalent, what BS 79 advises is when you plot a log normal, you normally take the lower tail. So the lower tail will give you your causative fracture toughness value. And then the second graph is those specimens that failed with a bit of data failure before cleavage occurred. Out of the 145, 2 of them were invalid, so we just ignore them. So we have 143. Again, another historical data set, which was done on a German nuclear vessel. This was in premise for the drafting of the master curve in the late 1990s. So the first master curve was actually published in 1997. So this was also a large data set done from room temperature up to minus 154. So in this case, we're looking at minimum of 3 equivalent. So we obey the rules of failing by cleavage and also, testing again with same macro structure. So we look at the core temperature testing where all the data set fail by cleavage. And again, we can see a good fit of the log normal distribution where our causative fracture toughness value will normally be the lower tail. And then for the fifth percentile with 75%, we don't need this much data set. Normally, about 25, 27 data sets will give you a good fit. But we had this on our disposal, so we've plotted all this. So if you consider price and time for testing, you don't need to test this much. And just for a comparison to the log normal distribution, which is a good descriptor of data scatter, we plotted also one of the probabilistic methods, the method of maximum likelihood. And as you can see, same data set, the 105 that filled by cleavage, the fit is not so good. So these are the causative values, as you can see. So for both the CTs and the SCMBs, if you take constraint into account, you can see the lowest temperature had the smallest causative fracture toughness value. And then we went ahead, say, okay, BS79 say use either the 50th percentile or the 20th percentile, but keep to this limit. So in keeping to this limit, we applied our method of 5th percentile, 75%. Then we perform a Monte Carlo simulation just to see the scatter using the same procedure. So specimen, number of specimen 3 to 15, for example, as it is in BS7910. And so with the 5th percentile, again, we can see our Monte Carlo simulation giving us similar values for what we obtained in with the log normal distribution. Again, for the reactor vessel, still is the same. We can see for the last data set, the 154, the causative value for the 5th percentile is just about 26, just like we got in the lower tail of the log normal distribution. And so, yeah, this simple simulation or this simple work has demonstrated that, we need to move away from the traditional practice. Those days in the 80s, people were not very versed in material testing. The materials strengths were different, and today the properties are different, so we need to move away from them. And also, if you wanted to take this into high integrity component, then we should consider the 5th percentile rather than the 20th or the 50th percentile. And so the idea is to get this across to the BS7910 committee, either to review the method or incorporate our suggestions into the BS7910. Okay, and I think that's so. Thank you very much. Just to say, this Professor Gao, which I mentioned, he was part from the beginning of drafting the PD 6493. And then later, Henrik also joined. So these people have coordinated and helped in, putting the paper together, which I'm presenting today.